So suppose f of x is a function defined at and near some specific point x0, or x naught. Naught is the English as in England word for zero. So this is a way of saying x0. I don't know why mathematicians caught on with using x naught instead of x0, but that's what we mean. And I'm putting a subscript on it to indicate this is a specific x value that I want to know what the derivative is. Then, the derivative of f at x0 at x naught is the value that can be approximated by I need to pick a number, let's call it t, f of t minus f of x naught divided by t minus x naught, where the approximation is more accurate or the approximation gets more and more accurate the closer t is to equaling x0, but never equaling itself. If t ever equals x0, then this fraction becomes 0 over 0 is suddenly undefined. But you can get as close as you want, and it is defined. And if, as you get closer and closer, these numbers get closer and closer to something, then that something is defined to be the derivative. And the notation we use for the derivative is the name of the function at the point. So this is the name for what is the value of the function at the point. We put an apostrophe to mean the derivative. This is sometimes pronounced f prime of the point. It's called the derivative of the function at the point x naught. You want to be careful when you're phrasing this. It's going to be tempting to say the derivative of f of x naught. But this is bad terminology because we always want to talk about the derivative of the function. F of x naught is a number. You can take the derivative of a number. It's going to turn out it's always 0, and it's not interesting. When we want to specify it's the derivative of the function, because the function is the thing that changes. F of x naught itself was always 4 in that context. The derivative was also 4, wasn't it? It's a bad example to use one where the y value is the same as the derivative. Yeah, we want to talk about the derivative of a thing that changes, and the thing that changes is the function, not the value of the function at that particular point. So that's the idea of a derivative. Notice that when we did those examples before, our t value was always bigger than 2. It didn't have to have been bigger than 2. The point was that t is supposed to be close to 2. And you can get close from two different sides. I can ask what was going on at t equals 1.99. I can take what's f of 1.99. In our case, it wasn't f, it was s. So s prime of 2 is about s of 1.99 minus s of 2 divided by 1.99 minus 2. What is that? That's 1.99 squared minus 2 squared divided by 1.99 minus 2. The number on bottom, I can subtract that. It's 0.01, but it's negative. The number on top, I probably need a calculator for. Hey, calculator. What is 1.99 squared minus 2 squared? Divide that by negative 0.01. Oh, the number on top is negative 0.039. And when I do this division, I get 3.99, which sure enough is close to 4. This is further confirming our thoughts that probably the answer is 4. This time I got a number a little bit less than 4 instead of a number a little bit bigger than 4. It's not always going to be the case when the approximation on the left is low and the one on the right is big. Usually one is high and one is low, but not always. It could be the case that they are both too high on both sides, but if you shrink them down, they are both getting smaller and smaller to the actual value. That's the idea of a derivative. We hit that in the first day. Let's try an example of this. If I hand you the function f of x equals 3 to the x minus 2x minus 6, and I say approximate f prime of -1, the thing we're doing is we need to say f prime of -1 is about, I need to pick a number very close to -1. So I will -1.001 or -0.99, that's pretty close to -1. And then I set up the same difference quotient. Difference of the y values over difference of the x values. How do I get these numbers? I get them by plugging them into this formula. Here's the weirdest feeling part of doing these computations is when I need to take f of -0.99, the way I'm doing it is as a plugging in. I plug -0.99 into this formula. But then the plugging in is happening both directions because that answer I get is being plugged into this formula. Like, that feels weird. It feels like, am I plugging this into this or that into that? It's going both directions in a weird way. The thing on bottom is what's -0.99 minus -1, that's positive. Come on. Positive 0.01. This f of -0.99 is what is 3 to the -0.99 minus 2 times -0.99 minus 6 minus, now what's f of -1? It's 3 to the -1 minus 2 times -1 minus 6. This minus means minus the whole thing, so I need parentheses around this. I can also put parentheses around this, but these ones don't matter because there's no minus in front messing things up. And now this is a thing that goes in the calculator. Hey calculator, what is 3 to the -0.99 minus 2 times -0.99 minus 6 minus all of 3 to the -1 plus 2 minus 6. In general, you should get an answer that's very small. I got -0.01, but I'm going to divide that by 0.01 to cancel it. And I get -1.63. Seems like the derivative is about -1.63. Do I know these digits are accurate? I don't. I have really right now no idea how accurate this is. If I wanted to know how accurate this was, I don't have a correct answer to compare it against, but the thing I can compare it against is an even more correct answer. I can plug in -0.999. Minus f of -1 divided by, I'm having trouble with my stylus here, -0.999 minus -1. This will be over 0.001. I'm not going to write that stuff out. A nice thing to know you can do is if you hit second enter, it'll retype in the last thing. Type it again, it'll retype in the thing before that. I want to type in almost the exact same thing, but with an extra 9 in here now. So here's the new computation. Divide that by 0.001. Now I'm getting -1.63359. What was the last one? Do I still have that up there? It was -1.63177. So the thing I've learned is that if I had written -6.317, those digits are probably not all accurate.